All right, hi guys, welcome back from spring break. Our first speaker today is Jiangmeng Zhang. She is a PhD candidate in electrical engineering at UIUC. She got her bachelor's degree from Xi'an University and master's from the University of Illinois. Her research interests lie in measurement-based power system monitoring, uncertainty assessment in power grid, and cyber-physical systems analysis.
Okay, thanks, Sumi. Thank you. Okay, so today I'm going to talk about the impact of tight coupling of cyber and physical layers in power grid. So first I'm going to give a brief introduction on cyber infrastructure in power grid, and also next I'm going to talk about what kind of model we are used in this analysis from the physical side, and with that we are going to look at the impact of the measurement noise as well as the impact of the measurement delay from the cyber layers on the power system performance. And here I'm going to focus on some interesting findings we have observed and some general math derivations and in a high level. But if you are interested in the detailed derivation part, I'm very glad to dive into that part if we still have time, or we can talk about that outline. And with that, I'm going to close that talk with some remarks. First, the cyber infrastructure in power grid. So traditionally, the power system has been monitored and controlled in a SCADA system. So this picture shows the main components in SCADA system. Generally, the excuse me. Generally, the IED intelligent electric devices will take the measurements in the substation, and then the measurements will be collected in RTU, remote terminal unit. And after that, the RTU will send the measurements through the communication network to the control center. And also it's the same way backwards. The control center will send the command through the communication network to the RTU, and the RED will, and then the substation will perform the command. And in recent years, and also the communication protocol used in SCADA system is called DNP3 protocol. It is also specialized in IEEE standard. Basically, this protocol specifies the application layers in the communication model. And also in recent years, PMUs has been implemented increasingly. And the system which utilizes the PMUs is called WAMS, Wide Area Measurement System. And again, this picture shows the main components in WAMS. So the PMUs in the substation levels will take the measurements, and then the measurements will be collected in the PDC. And then similarly, PDC will send the measurements through the communication network to the control center. And the protocol used in WAMS is specified in the IEEE standard as well. And both protocols all mainly focus on the application layers of the communication network model, and they suggest the Ethernet with TCP/IP protocols as lower level in the communication network level. And from there are many challenges arising from there. Firstly, the emerging of this kind of large volume data as well as various measurement-based applications present notable challenges on the communication network traffic. And also, although the TCP/IP protocol is suggested in this communication network, but that is mainly because of their dominance in the marketplace. Particularly, this TCP/IP protocol is not particularly designed for control systems, so there are many issues related to that, such as the measurements delay is random, is intractable. And also, as well, malicious attacks are always threatening. Basically, there are two kinds of attacks. one kind is the attack on the information accuracy, such as the false data injection attacks. Basically, it's the attack perform the man in the middle attack. They will get the information from the measurements and manipulate the measurements and send the false measurements to the control center. Another kind of attack is the attack on the timely delivery, such as the denial of service attack. Basically, what DOS attacks did is the attackers will keep injecting junk messages, packages into the network and occupy the network resources, so that the useful information cannot be transferred in a timely manner. And with that, in this study, we will focus on the impact of the measurements noise, which can be arising from the normal operations or maybe from the false data injection attacks. And also, we are going to look at the impact of the measurements delay, again, which may be from the normal operations in the communication network or from malicious attacks, like the DOS attacks.
It was very polite of you to sprinkle some Spanish words in there for your advisor.
Spanish? What is Spanish? I didn't see that.
One there.
Oh, really? Okay. Thanks. Okay, and then from the physical side, the power system model we used here first captures the electric network, the power flow equations, and also it describes the electromechanical dynamics. So here we are using a third order model to describe the machine's dynamics, like I put here. Note that the PCI here is the variable, which is a control variable the generator get from the secondary frequency control mechanism, which is called AGC, automatic generation control. Basically, the objective of AGC is to maintain the system frequency as at the nominal value, and also maintain the power exchanges between areas as their schedules value. And so what AGC did is AGC will take the measurements from the power system and then calculate the ACE, which is area control error. Basically, that's the mismatch on the frequency and as well as on the power exchanges. And then AGC will calculate the the control variable PCI based on an ACE. And then AGC will send the control command back to the power system. Actually, this is where the cyber impact comes in. So if the communication network is imperfect, then there may be the noises as well as delays on the measurements, and then which in turn will affect the system performance. And for the ease of presentation, from now on, I'm going to put all the network equations, dynamics, as well as AGC algorithms into a compact format, like x dot is equal to f, and g is equal to 0. And after linearization and as well as substitution, eventually we are going to get this ODE model, ordinary differential equation model, like delta x dot is equal to a times delta x plus the disturbance. And okay, so with all this system model, then we can actually look at the impact of the measurements noise. So first, in ordinary, the noise can be modeled as a white noise. So we put all the measurements which are used in the AGC as a vector. We call it eta. So we replace eta as eta plus the white noise here, and then we derive a stochastic differential equation rather than ODE model as we see in the previous slides. So it's like x dot will be equal to gamma 1 times x plus the white noise term. And so now here we have the stochastic differential equation model, but luckily there is a formula called Dinkins formula which can help us get the evolution equations on the state moments. And particularly we are very interested in the mean as well as on the variance. So from Dinkins we got these two equations on the dynamics of the mean as well as the covariance of the state. So here is very interesting. It shows that actually the white noise term did not show up in the dynamics of the mean. So basically, the white noise will not affect the state mean. But and also, if we look at the covariance equation here, also although the white noise term will affect the value of the covariance, but since it's only a gamma 2 times gamma 2 here, it is actually not affect the stability of the system. So so basically here we can say that the system is kind of robust to the white noise. But also from here we came up a tax scenario. So now let's say the merriment noise is not a white noise, but the noise intensity is a function of the merriments. So here the covariance will not be a constant, but rather than a function of the merriments here. And then with this new kind of malicious noise, the new covariance dynamics, then we can also using Dinkins, we got this new dynamic evolution equations. And here we are showing that basically the noise term will be a function of the covariance matrix. So by properly design this H function in the beginning, there's a possibility that the system become unstable. And even for a very simple linear function, let's say the noise intensity is just proportional to the merriments, is equal to alpha times the merriments. And later in the case studies, we are going to show that the system is also going to be unstable with a very small place.
So just to clarify, because people might get confused, when you're talking about stability of the system, it's the stability of the dynamics driving describing the evolution of the covariance matrix, not the evolution of the linear DA model, correct?
Right.
Yeah. Just to make sure that people follow that. When it refers to of the system, it means to that linear dynamics that it has up there, and then the same thing down there in the second bullet. When it says the system may become unstable, it's referring to the dynamics of the covariance matrix.
Right. So also I'm going to talk about it like in a moment, but basically if we want a stochastic system to be stable in the sense of absolute surety, then we want the system is stable in terms of the covariance. So what I'm saying is that as long as this system is stable, meaning the state covariance is stable, then the system will be stable almost surely. Okay, so let's look at the numerical results. The first two here shows that this is what happens with when the noise is just white noise. So the blue line here shows the result from Dinkins formula, and the white lines here showing the result from Monte Carlo simulation. They match with each other pretty well, so which verifies our method. And then if we look at the sample path here, we are showing that although the frequency varies, there's derivation on the sample passes, but the variance will be bounded by a value if the noise is white noise. Here we are showing that if the noise is malicious noise, meaning the intensity of the noise is proportional to the merriments. here we are showing that although the mean still stays constant at around 60 Hertz, but for every sample pass, we are showing that the frequency actually diverge a lot. It's going like far away from 60 Hertz. The feature about this, do you have questions?
Yeah, I see what sample path.
Sample path is, so here the noise is white noise, so it's a random thing. And when we do Monte Carlo simulation, we basically sample the white noise, and each time. So for each time, that's one sample path. Yeah. Yeah. So the feature about this kind of attack is basically the measurements are manipulated in a random way, and also the noise is kind of the malicious noise is kind of in disguise of noise. So the traditional bad data detection method may fail about on this kind of attacks. So also we are going to here we are going to look at the impact of the measurement delay. And to do that, we have to reformulate our model a little bit, because in reality, the AJC only operates in a discrete time, because it takes the measurements in a discrete time. So so now the AJC dynamics will become will be described in a discrete time system like this, and the delta T here is the sample rate. And also, if we combine the system dynamics as well as the AJC dynamics together, we got this kind of hybrid dynamic system. The continuous time part describing the system dynamics, which should be in a continuous way, and the discrete time part describes the AJC dynamics. And after discretization, we can convert the first part, the continuous time part, into a discrete time part, and then we put them together. We got this compact form, which is a discrete time dynamic system. And it's very interesting to show here that basically the phi 1 here is the system matrix for the original power system without AJC. And the B2 here is equal to 1 minus delta T. So it's meaning that although the original system is stable without AJC, but if our time interval is too large, then this system matrix maybe become unstable, meaning that the largest eigenvalue will be larger than 1. Okay, so yeah, as a background, basically, if we want to determine whether the discrete time system is stable or not, basically we look at the system matrix A here. If the largest eigenvalue is larger than 1, then we are going to say that the system is unstable. And okay, so this is the system model without measurements delay. And if we consider the measurements delays, it will become a little bit complicated, a little bit more complicated. So again, this is the AJC system, and at the time here, if the new measurements is taken, but actually the new command have to wait for time t until the new command arrive to the generator and take effect. So there will be a time delay between the new measurements is taken, whereas the time when the new command arrives the generator and take effect. So in that case, basically for one time interval, there will be two parts. The parts before the new command arrive and the parts after the new command arrive. And also, then based on that, if we discretize the original system, then the new discrete time system will become like this. Basically, it shows that the system state at the next step will not only depend on the current state, it will also depend on the previous state. And again, if we put all the equations in a compact form, we got this new equations here. And also we can determine the system stability by looking at the largest eigenvalue of this system matrix phi here. And so here is some interesting findings from the numerical examples. This one is as I said earlier that the x-axis is the sample interval, the y-axis is the largest eigenvalue. So if we keep increasing the sample interval, basically the largest eigenvalue will also increase, meaning the system become less and less stable. And another interesting thing about this is if we fix the sample interval and we change the time delay. So if we increase the time delay, actually the largest eigenvalue is not in a linear way with respect to the delay. So it shows that it seems like sometimes the Merriman's delay actually help us mitigate the system instability. So because like in this certain range, when the delay increases, but the largest eigenvalue actually decrease. So that is kind of counterintuitive that the Merriman's help mitigate the system instability. But is this going to help us or not? Like, let's see, like with the random delay. So because in reality, as I said, because of the protocol, the real Merriman's delay is not deterministic, it's kind of random. So in that way, all the delay we are talking about here, the time delay here, will be a random variable. So as well as this system equation will be a random stochastic system. So in order to investigate the stability about that system, first we can take the expectation on both sides. And we got this dynamics equations for the state mean. And we know that if the largest eigenvalue magnitude of this matrix is larger than 1, then absolutely this system is going to be unstable. But know that this is kind of from the attack perspective, saying that if we can make this the eigenvalue of this matrix larger than 1, then the system will be unstable. But the reverse is actually not true, because if we want to make sure the system, as like we talked earlier, if we want to make the system is stable almost surely, we have to ensure the system is mean square stable, meaning that we have to look at the dynamic equations on the system covariance and make sure this system is stable. And it's kind of messy equations, but anyway, so eventually we have proved that if we want to make sure this system is stable, we only need to look at the largest eigenvalue of this matrix is the expectation of phi 1 times phi of phi times phi. The time here is actually a operator called Kronecker operator. So anyway, so the largest eigenvalue of this matrix will determine the whole matrix, the whole system stability. And with that, let's go back to our previous question. So from this picture, it seems like sometimes the Merriman's delay will help us mitigate the system instability. But actually, if we consider the delay as a random variable, as a normal distribution random variable, and we take the mean at 0.2 seconds, and then we vary the variance of this delay. So we are showing that here it shows that basically the system is kind of stable in terms of the variance. So if we increase the variance, the largest eigenvalue magnitude is kind of is increasing, but not that fast. But whereas if we look at the mean is at 1.6 second here, and also we change the variance of this random variable, and the largest eigenvalue looks like this. So with very small variance on this delay, actually the system is going to be unstable. So which saying that although when the delay is deterministic, sometimes the delay may help us reduce the largest eigenvalue, but actually at this point the system is very sensitive to the randomness. So if there is a little bit variance, then the system is very likely to become unstable. And also this is another simulation result showing that if the delay is at 1.7 seconds, deterministic, then the system is stable like this. But when the delay is random, also with mean of 1.7 seconds, but a small variance, then the system became very unstable. Like the frequency is far away from the stable point. And the feature about this kind of event is actually the attacker is kind of easier for the attacker to perform denial of service attack. And also for this kind of attack, there's no model parameters are required. And okay, so with that, the conclusion is all the kind of interesting findings showing that the full impact of the tight coupling of cyber and physical layers is kind of critical and hard to anticipate. So which suggests that carefully attention should be paid when we implement new information technologies as well as new control algorithms. Okay, with that, thank you, and any comments? No, survey. What kind of what? This is the disturbance. The disturbance is from the load. Yeah, I changed the load by like 5% or 1%. So that's the disturbance. Yeah, please, Shrikant.
Is there an intuitive understanding on why there should be system instability because of the increase? Because if you go beyond a certain measurement delay, you see instability.
Yes.
Is there any physical understanding of why it should happen? Is it because of the effective damping of the system comes down, or is it because of some other reason the system goes unstable?
You mean why here it's become unstable? It's like a. So it's like generally the system transient is like this. It's like this. So it might be possible like when at this point the measurements is taken at this point, and the command is calculated to reduce the frequency at this point. But after with the measurements delay, actually the new command is performed at this time when the frequency is already very low. But the command is actually the purpose of that command is to reduce the frequency at this time. So so that's why with certain measurements delay, the mismatch with the original system may make the system worse. Yeah, please.
I guess this question kind of goes along with your talk.
Yeah.
So how do you think this would scale to a larger system? Because you only have 2 buttons.
Yeah, for bus system.
Would it be like 25 seconds for a larger system? Like if you did I don't know what kind of bus, 12 bus, still 1.6 or?
Yeah, that's a good point actually. So originally with the conventional power system, that this depends on the system inertia basically. So if the actually it's very interesting. So for now the AJC, the time interval for AJC is 2 to 4 seconds, but with this small system with small inertia, at 2 seconds the system is already unstable. So that's related to the system inertia. If for a large system the system inertia is large, then sure, like maybe it will take like a longer time to make this system unstable. But again, back to the current state, there are more and more renewable energies in the power grid, which making the system inertia keep decreasing. And with that considered, it will possible that in the future maybe the AJC will become kind of dangerous to this kind of problem. Any other questions? Okay, thank you again.
It's okay, it's fine. I don't have enough time already. It's okay. I can present them.
Is this one?
All right, our second speaker today is Enver Candan.
I think this is off.
Yeah, I think it's on. So Enver received his BS degree in 2012 from Istanbul Technical University in Turkey with a double major in electrical engineering and control engineering. He's currently working towards his master's degree at the University of Illinois under Professor Robert Palawa.
Thank you. So the title of my talk is Series Stack Power Delivery Architecture for Data Centers, and this is the work that I have been focusing for roughly around a year. So yes, this is the outline of my talk, that I will give some introduction about the data centers and the servers that we focus on, and I will talk about differential power processing. I know you listened that differential power processing talks for a long time, so I will keep it short and only focus on the one that I'm using. I hope it won't be boring for you. And after that, I will talk about the bidirectional hysteresis control that I developed for a system-level control in server to virtual bus architecture. And I will give simulation and experimental results showing that this control and this architecture is well fit in data centers. So yeah, Josiah talked about that a few weeks earlier as well. So we know the data centers are growing really fast, and their energy needs also increases day by day. And an average data center has a PUE of 1.8, which means that almost half of the power that comes to a data center is actually consumed by the servers. The other half is consumed by other IT needs, or like some part of it is wasted during this power conversion process until the power reaches the servers. So as you see here, there are several power elements that power needs to go through before it reaches the servers. And this is an example of DC distribution architecture for data centers that we focus on. So I mean, all these transformer, rectifier, UPS, and DC-DC converter units are common in this kind of architecture. So that's why in this research we focus on alternative ways to distribute power and regulate the voltages, regulate voltage for servers after this point. So from now on, I'm going to assume that there is a well-regulated DC bus exists in this point, and I mean this is already the case in nowadays data centers. And I will look for if there exists a more clever way to do power distribution after this point. So this is again the example of DC power distribution in data centers, that each server has its own DC-DC converter that converts bus voltage to server voltage. This architecture is very reliable for in terms of power delivery for operation conditions such as server or converter faults or startup, like hot swapping. I mean, for any condition, any real life condition that's the case in data centers. However, here the problem that we try to, or the improvement that we want to introduce is that here, since each server has its own DC to DC converter that converts bus voltage to input server voltage, this converter needs to process all the power that's consumed by the server. And normally this is typically like 380 volt, and this is typically like 12 volt. So there is a large voltage step down on this converter. And when you consider the number of the servers in a data center, you lose so much power during this power conversion stage. So to overcome that, a previously suggested idea by Professor Crane and his former PhD student Pradeep Shenoy is stacking these servers up and connecting them in series to avoid voltage step down from bus to server level. I mean, when you connect them in series, that you use their voltage domain to build up the bus voltage, and you can. I mean, in this case, you take care of the voltage step down ratio, but since the serially connected servers, the serially connected elements need to conduct same amount of current, in case of a power mismatch between servers, their voltage will vary. And you solve this problem with introducing differential power converters at these intermediate nodes. Here, the differential power converters inject or reject current mismatch between, or the power mismatch between the servers. And you are, I mean, this is shown that you are able to regulate the individual voltage domains by using differential power processing. Here, the main advantage is that these differential power converters do not need to process the bulk. The power that the servers consumes, they only need to process the power mismatch between servers. So the bulk power is still provided by the bus, which is normally the case. I mean, the existing case in data centers. And here you have significant amount of reduction in the power processed, as well as the power lost in the conversion stage. So again, when you consider the number of servers in data center, here you can improve the system level efficiency significantly. So in my control algorithm, they don't.
Just controlling voltage?
Yes, exactly. So I will talk about the algorithm that I developed. But I mean, we desire no communication between servers, and with the preliminary results that I obtained, that I'm able to regulate these voltages without communication. So I am going to directly jump to server to virtual bus topology of differential power processing, and I'm happy to talk about why this is the one that we choose among the other strategies. But I don't want to just. I mean, I have backup slides if you want me to explain. But this is basically that the server to virtual bus architect. Okay, so let's start with what is virtual bus. This is a new term maybe for most of us. So what I mean with virtual bus is a capacitive bank, like that's connected in parallel with all these isolated converters, so that this creates an environment for every converter here, for every converter to exchange power between each other. So the main advantage is that here that only the server who has the power mismatch, only the converter whose server has the power mismatch needs to work to compensate that power mismatch, as long as the virtual bus voltage is within our safe limits. Okay, and the main disadvantage of this architecture is that you need to regulate this virtual bus voltage as well, so that it will not going to explode. This is a capacitive bank. You need to take care of that as well. So here, the main question is that how do you rate these converters? And to consider real data center operation, which sometimes you need to do swap circuits or swap servers, or I mean, there may be some faults or startup shutdown issues. We rated these converters at full server power. However, as I told you before, these converters only need to process the difference power between the servers, so they need to be able to work efficiently at light load. So one common control method for improving light load efficiency is hysteresis control, which is the one that I propose to use here. However, the hysteresis control is traditionally used to keep one load voltage within limits, while here each converter has two voltages that he needs to take care of. So this is what I'm going to explain next, and as an objective that we would rather that each converter will implement some local control. There won't be any communication between converters. So before introducing this hysteresis, bidirectional hysteresis idea that I propose here, let me model the system. To avoid switching action, I just model the DC-DC converters, bidirectional isolated DC-DC converters with these two current sources that are connected reversely. And I just name this IDC1 and IDC1 prime so that there is an efficiency term introduced here. So if I shoot a number for here, I shoot another a relevant number here considering the efficiency and the direction. And also the server, I model the servers as controllable current sources. And since the server board has huge input capacitance, not huge, okay. I also connect the capacitors in parallel with them, and so here, I mean, this is the hysteresis shape that I propose. So we have for each converter. We have two different voltages to take care of to keep within some safe band that we desire. So how it works is that let's ignore this for a while. Let's assume that there is a power source here. Just ignore this virtual bus. At some certain sampling rate, I'm sampling this server voltage, and I compare this with a reference, which is 12 volt in this case, and I calculate an error, how far I am from that voltage, and depending on that measurement, that error, I'm going to decide if this voltage requires current injection or current rejection, or maybe it's in the safe band limit, so it doesn't really require any current injection or rejection. And after I did this within the same control interrupt and same sampling rate, I do same comparison for virtual bus. So each converter is able to measure this virtual bus voltage and also its own server voltage, and I am making this comparison for both server and virtual bus inside the microcontroller of each converter. And since each server voltage or virtual bus voltage can be in normal state or current injection state or current rejection state. I call them as states, but that's their need basically. For each converter, there are 9 possible states that we can be in. And for example, let me start with the normal case where neither virtual bus or the server they don't require any current injection or rejection. In this case, I keep the converter off and everybody is happy. Another possibility is that the virtual bus will be within predefined limits, while the server will require current injection or rejection. In this case, I can turn on the converter in positive or negative direction, which I refer with this arrow here. So if the server requires current injection, which means that its voltage is low, so that I decided to inject current to that node, I can turn this converter on in positive direction. Since the virtual bus is in normal state, within predefined voltage limit, this will not make virtual bus unhappy. Same for current rejection. If this guy requires current rejection and if this guy is happy about this state, I can just turn it on in the minus direction. It's very intuitive. Same thing for assuming the server is in normal state, it is in the predefined voltage limits. And the virtual bus requires current injection or rejection. In this case, I can turn it on in minus direction if this guy requires current injection, or positive direction if this guy requires current rejection. These are all intuitive results, as well as these two, where while server is requiring current injection, the virtual bus will require current rejection, so I can turn it on in this direction, and this is also intuitive. While these two left here seems a little bit dangerous or tricky, which is like both for each converter, both server and virtual bus will require current injection. In this case, I turn back to basics and rely KVL on in this loop, which means that the sum of all server voltages here is fixed to this bus voltage. And if, let's say that this guy's voltage is low, which means that I need to inject current here, while I need to inject current in virtual bus as well. If this guy is low, there will be at least one of them will be high, or at least one of them will be in normal state, so that when the virtual bus will require current injection, the other, at least one of them will turn on in the minus direction and take care of virtual bus's need. In this case, if I keep this guy off, if I keep my converter off, the current increase on this converter will increase the bus current, and this will take care of this voltage. I am not sure if it's a good explanation or not. I can talk about it more. I want to give the simulation results. So this is the simulation model that I built in Plex. So I have load current, measured server current from a server in our lab. I just feed this to these different currents to these controlled current sources, and these are my mathematical model of my differential converters, which you see here. There is a C script that reads voltage from both sides and determines which direction I need to turn it on. And I also, to introduce some dynamics, I also make a first order system response here, so that it will have a dynamic. It will not be just, to have a more realistic presentation. And in addition to that, I am also going to read the voltages and decide converter efficiency of, decide currents, so that the converter efficiency is 90%. Because if you assume that this is like 100% efficient, the voltage in virtual bus will never will never go high or low. So this is the server currents that I take, that I used in my simulation. And these are the differential currents that I inject or reject. So again, positive direction means current injection to server. Negative directions means negative direction means current injection to virtual bus. So let's zoom in this and see that how these differential currents look like. So you see that I'm able to achieve on-off control. And also this is zoomed in version of this part, and you can see the dynamics here. This is the rise time is around 100 microsecond, and this is the virtual bus. This is the server voltages that my predefined voltage limits are plus minus 0.10 volt. So you see that with this idea, I'm able to keep the voltages within predefined limit, and this is virtual bus current and bus current. So of course everything works on simulation. Then after we obtain these results, the control algorithm seemed promising, and we started to think about on hardware. So this is the converter that I built. This is not. Maybe you are not familiar with it, so I want to take some half a minute to explain how it works and stuff. This is not. It's not a new, but it's not common. It's not a common converter. So here, this is called dual active bridge. You have two bridges and an inductor in between, and the galvanic and the transformer to create isolation. So S1, S4, and S2, S3 are complementary signals of each other every time, and they are at 50% duty cycle. Same as S5 and S8, and S6 and S7. They are also complementary of each other. And how you do voltage power transfer is introducing a phase shift between this bridge's gate drive signals and this bridge's gate drive signals, which is shown here with phi. And depending on the direction of phi and the amount of phi, that you are able to transfer power in both directions. and this is normalized power curve. So you can see that you can, it is quite symmetric. This is basically how it works. So this is the one that I built. This is the dual active bridge that I built. This is the efficiency curve of that. It is like mid 90s. And this includes all logic signals and all gate drive signals. This is not only power stages efficiency. And this is the rise time and fall time that I showed, which is quite important for hysteresis control. This is, I turn on the converter, and I turn off the converter in one direction, and I turn on in the other direction and turn off that one. So this has like almost 100 microsecond, 150, 120 microsecond settling time for both turn on and turn off. It's quite good performance for what I desire. This is my experimental setup that I again get current, real server current. We measured that and we play that back with these signal generators in these electronic loads. So we are able to repeat same experiment one after the other. These are my 3 converters, that 3 dual active bridges that I built and connected them here. You can see, and all measurement stuff and all required other equipments. So this is one experimental result that I want to share. This is as I told you, that the measured current data that I scaled it down so that I will be able to. Okay. So first, maybe I should say that I'm turning on the converter at its maximum, at its most efficient point, which is around 30 watts, kind of. So I scaled down this data so that I make sure that my circuits will not blow up because I spent so much time on soldering them. So of course I'm eager to just extend the power level, but I needed to get results first, some preliminary results. So this is the server that changes its load and to a higher traffic and lower traffic, in some sequence for like 80 seconds. And this is again my predefined. So here my predefined voltage limits are plus minus 3 volt, plus minus 0.3 volt. So I am able to achieve that for all 3 servers, electronic loads, which emulates server behavior. And this is the virtual bus voltage. For virtual bus, I said I can be more generous. My hysteresis band is plus minus 0.6 volt. So as you can see that this guy also stays within limit. So yeah, this server to virtual bus DPP is proposed and demonstrated with some bidirectional hysteresis control method. And it enables to regulate both server and virtual bus voltages at the same time. I will extend the control idea and the hardware, my hardware, for all system operation conditions, such as like initialization. Here I didn't really show any initialization. I will consider that as future work. I will look for hot swapping options and like server failure scenarios and stuff like that. And the further goal is like conducting same experiment with real servers. So thank you. That concludes my presentation. I can take questions.
Did it ever explode one?
No, not yet.
No. You can add that 1.7 second delay.
Yeah. Okay. Yeah. Yeah, Chris. Yes, this one. Yes.
Is that like interrupt delay or?
No, it is not. This is okay. So this I have. Let's say that I have this virtual bus capacitance away from these onboard capacitors. When you turn it on, instantly the first spike is created in this capacitor before it even arrives to this virtual bus. I will talk more about that in group meeting. This is very simplified answer, yeah. But it is not. This happens within one control cycle, and at next control cycle, the control algorithm just takes care of that, and the voltage drops.
And you're running all 3 of these controllers on one microcontroller?
Yes, so far it is. Yes, unfortunately, I don't have one microcontroller for each of them. the only thing that I don't use this guy's voltage measurement to decide this if I need to turn on or off this guy. The only thing that here the PWM signals, if I apply PWM signal to both converters, they are synchronized. This is the only thing that looks like central converter. Otherwise, the decision made is independent of each other. So far, to simplify, I use same controller. Yeah. Yep.
You control the traffic of each server. I mean, I just like thought it's maybe like you need different smart
Yeah, this one I don't know. I mostly focused on hardware stuff so far. I didn't really have a chance to look for this traffic control and stuff. Josiah is more into it. Maybe he can reply.
Yes, there is. No, a lot of things for it.
The answer is no, only if you assume that your software always works. I wouldn't trust my Windows PC to always work in regular software. Well, Linux and any PC, right? That's where you need the hardware backup.
Anyone else? Okay, thank you.